The kinetic and molecular theory of gases states that the majority of the volume occupied by gas is empty space. And while these gas particles are moving, they appear to be moving in a random motion, but in fact, each molecule continues to travel in a straight line until it collides with another gas particle. Otherwise, it exerts no force on any other molecule. And when it does collide, these collisions are elastic. You might have noticed above I wrote down random in quotations. It's just to emphasize that it appears to be random, where in fact, because there are billions of gas particles colliding with each other, it may appear to be random when in fact each collision is an elastic collision. In fact, if it wasn't an elastic collision, then we'd have a problem with the next statement, which is that the temperature is based upon the average kinetic energy of the molecules. So if we started losing energy in the gas particles, that means the temperature of the gas would rapidly drop, meaning that while you're watching this video, you quickly freeze to death. Let's review through Boyle, Charles, and Gay-Lussac's ideal gas laws. Boyle's law states that if you increase the pressure of a gas, its volume will decrease. You've probably tried this before with disposable water bottles, where the moment after you've emptied out all the contents and you capped the lid, you tried squishing the bottle, and it appeared to be very tough. But if you tried hard enough, the volume will decrease. And as the volume decreased, the pressure inside the container increased. That's why when you let go of it, it wants to restore itself back to its original shape. Charles' law states that when you increase the temperature on a gas, its volume wants to expand. In fact, the opposite is true as well. If you decrease the temperature of a gas, its volume will want to decrease as well. You can see that in this video.
Hi, I'm Joanna.
And I'm Steve.
And this is a container of liquid nitrogen.
And this is a really big balloon.
Let's see what happens when we place the balloon in the liquid nitrogen.
Okay. Whoa, wait. Isn't the balloon gonna pop?
We'll see.
Oh, man. Huh. Okay, so the balloon didn't pop. There's obviously a hole in the balloon somewhere because the air's leaking out. So maybe instead of popping, maybe the balloon just got really cold and it cracked like an egg, and all the air is slowly leaking out of the crack.
Well, if that's the case, what's the balloon going to do when I take it out?
Nothing. It's a balloon with a hole in it and all the air's gone.
Well, I'd say the air is still in the balloon.
So where's the air?
Right there.
That's water.
Nope. If that were water, it'd be frozen solid. That's liquid air.
What?
When we place the balloon in the liquid nitrogen, the air inside the balloon gets really cold. When particles of a gas get cold, they start to slow down and take up less space. If we can get the gas cold enough, we can change it from a gas to a liquid. That's what happened inside the balloon. We changed all the particles of nitrogen and oxygen to a liquid.
So how do I get my balloon back?
We just have to place it someplace hot, like the table.
Oh, so I get it. Now the reverse is happening. The heat from the table is making the liquid air inside boil. When a liquid boils and changes to a gas, the particles move faster. When the particles move faster, they take up more space, and the balloon gets big.
Exactly. Thanks for watching.
Gay-Lussac's law states that when you increase the temperature of a gas that's confined in a container, the pressure will want to increase. This happens all the time with car tires, where as you're driving, the frictional forces generated between the tire and the ground cause the gas temperatures to increase. Consequently, the pressure inside the tire increases as well, giving you an elevated reading. Whenever you're trying to measure tire pressure, you're supposed to measure it when the car has been sitting around for a while, where the temperature of the outside matches up with the temperature inside the tire. Now, when you combine all three laws together, you come up with something called the ideal gas law, but more on this later. Avogadro's number is a crazy huge number. It's 6 followed by 23 zeros. On the AP exam, they'll write it out like this. In fact, there's a formula that goes along with it. But what does this all mean? Let me put it to you this way. If I so happen to have 600 sextillion hydrogen atoms all put together and placed in a container, I now have 1 gram of hydrogen. Or if I had 600 sextillion helium atoms all grouped together, I now have 4 grams of helium. Or if I have 600 sextillion lithium atoms all grouped together, that works out to 7 grams of lithium. So this Avogadro number, it's a conversion ratio. It's like converting between feet and miles. What this number tells you is that if you have that many quantities of that particular element, it'll work out to a particular mass. And where do we get these numbers from, this 1, 4, and 7? Well, that all comes from the periodic table. Check out the atomic mass of all of these elements. So for example, if I happen to have 600 sextillion aluminum atoms, that would work out to roughly 27 grams. So that's how you would use this number. As for the ideal gas law, we know what P means, we know what V means, we know what T means. And we have just learned which is the number of moles in that gas container. But what does R mean? Well, R is a constant. It's known as the universal gas constant. Now this formula is fine if you measure quantities in moles, so in large quantities of atoms. But what if you want to measure everything with just one atom, or a handful of them? Well, then we wouldn't be counting in moles, we'd be counting in number of atoms. We would be using this constant instead, and this constant is known as Boltzmann's constant. On the AP exam, they'll provide both equations, like so. Now they won't expect you to do any calculations with these formulas, but they would expect you to know what every term means and how to incorporate them into a problem. Let's suppose we have 3 balloons, each of them filled up with 1 liter of that specific gas at its particular STP, or standard temperature and pressure. Here are 2 questions. Which balloon has the most number of moles of gas, and which balloon has the greatest mass? The correct answer for the first one is D. All balloons contain the same number of moles of gas. This is one of the properties of gases, where regardless of which element you're talking about, all gases consume space at the same rate. As for the second question, which balloon has the greatest mass? The answer is carbon dioxide. After all, if you look at the atomic mass of 1 carbon and 2 oxygens, it far outweighs neon and hydrogen. Here's one more bonus question. How many moles of gas are there in each balloon at standard temperature and pressure? The answer to this question will be provided for you at the end of this video. As discussed earlier, a single gas particle does not have a temperature. You're actually measuring the average kinetic energy of them all. This kinetic energy can be used to describe why diffusion exists, because gas particles are constantly bumping into each other, and they're transferring their energy from one molecule to the next. These collisions are all elastic, so there's no energy lost, but there is a catch with it. It is possible for one molecule to lose its energy to transfer that energy onto the next molecule, thus speeding it up. However, the overall energy of the system remains the same. And we can see that in this diagram over here. Let's focus on the blue curve. What it tells us is that at room temperature, there will be some gas molecules moving really quickly, close to 1200 meters per second. There will be others that are moving very slow, even possibly at 0 meters per second. However, if you look at it as an average, on average they're moving at roughly 400 meters per second. And with regards to the red curve, it's emphasizing that when temperatures reach closer to 900 degrees Celsius, the gas particles are moving much faster, closer to 800 meters per second. Now there will be some moving very fast, over 2000 meters per second, but there could also be those that are moving very slow, close to 0 meters per second. So in other words, if you had a container of gas sitting in the corner for many years, it is unfair to say that all the molecules are moving at the same rate. There will always be some moving faster, some moving slower, but overall they have this average value, and that's what we measure as temperature. So how do we create that formula on the left that describes the average kinetic energy defined by the different temperatures? Well, we know that the gases are all contained inside a box. So we'll talk about one box and one atom moving. If we were to calculate the time for the gas to move forwards and backwards, that would be defined by the distance over speed, or L over V. And since it travels both forwards and backwards, we need to double that time. That's why the formula is 2 times L over V. Now when it collides off the wall, this results in a change in momentum, or an impulse, where impulse is equal to force times change in time. Again, when the gas molecule bounces off the wall, the direction of its velocity changes, so this formula simplifies down to this. Now this is happening in all 3 dimensions. So if we're taking a look at the average kinetic energy, then we need to take all 3 dimensions into consideration, and we need to divide by 3. Next, Since pressure is equal to force over area, we can write the formula as so. And if we bring up the L on the bottom right hand side up, we get L cubed or V. You'll notice on the right hand side we have m times v squared. And kinetic energy is 1/2 mv squared. So why not make it look like that? Because in this statement over here, we can redefine 1/2 mv squared as kinetic energy and simplify as necessary. So this is how the formula is created. For the purposes of AP, you don't really need to know how the formula is created, but it's nice to know that it came from some form of mathematical rationale. You'll also notice that the value of k is not just k, but k-RMS, where RMS stands for root mean squared. It's another variant of an average. So what exactly do you need to know for the AP exam? Well, this is it. The average kinetic energy of a system is an average of the many different speeds of the molecules in the system that can be described by a distribution curve, which you can see on the left. And B, the root mean square speed corresponding to the average kinetic energy for a specific gas at a given temperature can be obtained from this distribution curve. That's all you need to worry about. So even though gas particles may be moving at very high speeds, such as 500 meters per second, because of the billions and billions of collisions, this overall slows down the rate of diffusion. And we know that this must be true due to the example listed below. The internal energy of a gas can be defined by this formula here. So only the quantity of gas inside a container and its temperature affects its internal energy. So let's create this formula from scratch. We know that the internal energy is equal to the average kinetic energy of that one particle of gas times the number of gas particles inside the container. And since k-RMS is equal to 3/2 times Boltzmann's constant times time, we can sub that into the formula. We'll get rid of Boltzmann's constant and convert it into Avogadro's constant, and then we finally arrive to the equation that was listed above. Again, you don't need to know how to derive this equation, but know that this equation is used to describe the internal energy of a gas in a container. You don't need to derive the equation. All you really need to know is that the quantity of the gas and its temperature are the only two factors that affect its internal energy. Here are a few check your understanding questions. You may pause the video and think about your solution before continuing. Ready for the answer to number 11? The answer is less than. The answer to question number 12 is no, because you need to measure the kinetic energy relative to temperature in Kelvin, not in degrees Celsius. So in this case over here, you need to add 273 to 50 and 273 to 100 to properly solve for this problem. Now on the other hand, if it did double from 50 Kelvin to 100 Kelvin, then yes, this statement would have been correct. Number 13, the answer is unchanged. Both of those cancel each other out. Number 14, argon has the greater temperature, and it has to do with the fact that if you look at the molecular mass of argon, it's 10 times heavier than helium, so therefore it has 10 times more kinetic energy while in motion. This actually brings up another important point. If you double the speed of the gases, does the temperature double? And no, the answer is that if you double the speed of the gases, then the temperature will increase not by double, but by 4 times, because it is a quadratic relationship between speed and average kinetic energy. And the answer to that bonus question is 0.045 moles. Stay tuned for the next episode.